Good morning. In this chapter, we're going to discuss electric field, and we're all set up to do that because we know the mathematics that we are going to use. We have established what curvilinear coordinate systems are. We have looked at different operators such as divergence, curl, gradient, and how they appear in different coordinate systems. So let's take a step back and go back to motion or mechanics, right? Where you studied about Newton's laws. So essentially, Newton's law is the second law is that force changes momentum. F is equal to dp by dt. So to understand momentum here, we need to go back a step back and think about what happens when objects move. So for example, let's say we have two identical ice cubes. Let's say these are two identical ice cubes. Let's call this A and let's call this B, but they're identical except for the names. And let's say I push this ice cube. Then your common experience, your sense experience tells you that this ice cube is going to probably move here, right? So after I push the ice cube A got something that B didn't have. So it became different. It's no more identical because it went to a different place. It went from its old place to new place. So it got something that it didn't have before. So this is where we talk about the important concept of impetus. So this impetus is the cause of locomotion. And what is this impetus? It is a power. It is a category of quality. So let's write that down, right? So what is impetus? It's a property activated in a body that moves it at a constant speed in particular linear direction. So impetus is a quality, and it is second nature to the body. What do we mean by that? For example, if I am walking, for example, then my nature itself doesn't change because of that walking. Or when the ice cube is moving here, it is still ice cube, right? So this impetus is second nature to the body, and the proper way to say why it is second natured is because it can either be gained or lost. I can either gain it or lose the impetus without changing the fundamental nature of the body. For example, here when I pushed on this ice cube A, I didn't change its fundamental nature of what ice is or what anything is. But nonetheless, I gave it impetus, and that impetus led to change in its place, locomotion, and that's how we are able to see that this block A is different from block B. So this momentum that we use here is a measure of impetus, which is the cause of motion. So if I ask the question of what is causing the motion, right? So if I ask the question of what is causing the motion, the body has a property in it. It's a massive substance. This body has mass. Mass is also a quality. It is extended. So this substance is existing by itself, and it has its properties, and it moved because it could either gain or lose impetus. So when I acted upon it, it gained that impetus. this ice cube, so it moved in that direction. So it is the immediate cause of the motion was impetus. But where did this impetus come from? This impetus, this push on the ice cube did not come from nowhere. I pushed it, right? So I pushed it. And so there is a force that was applied by me, and that force led to change of impetus. And that's what Newton's second law is. So this ice cube A has this quality, a property of the ability to have impetus, and by applying this force, I'm activating that, and that impetus can be gained or lost. So by gaining that impetus due to the application of force from me, the ice cube A moved. So when we ask what is causing the motion, we need to think about different types of causes. So there are different types of causes. For example, let's look at these different types of causes here briefly. So we have material cause, that is what makes up a substance, and I will give you an example that makes it easier to understand. And the second thing is formal cause, and then we have efficient cause, and then the final cause. And also we have proximate cause and remote cause. So when we are asking ourselves what is causing motion, we need to understand what cause we are referring to, right? So in case of the ice cube A, right, then I said that impetus is the cause of locomotion, because that impetus is what is making it move. But the remote cause for impetus, why did this get an impetus? Why did this object A get that impetus to move in this direction? The cause for that getting that impetus is the force. So force is the remote cause. Through force, I'm changing the impetus, which is the proximate cause. So impetus is the proximate cause that's actually moving the body, and force is the remote cause, which in turn changes the impetus. Now let's talk about these causes: material, formal, efficient, and final causes. To do this, let's take the example of a house, right? So if I have a house, let's say, so the material cause is the material that makes it up. So whatever material, the bricks, the cement, and the wood, whatever is used to construct it. And what we mean by material, it is same thing as physical. That is, material is something that is changeable. It is something now, but it can become something else later. So if I take a house, the material cause of the house is bricks and cement and wood. Whereas the formal cause is the way it is. You know, it has four walls, for example, right? It has a roof. You know, it is in a particular way, in this particular fashion, and that's why it's able to stand that way. But what is the efficient cause? Is who built it. So some builder, some contractor built the house. Why did he build? Well, I paid him to do so. I wanted a house, right? So I wanted a house, and so I got a builder to build it, and that builder had a design to build it, and then he used the right materials for the right things and actually built the house. So if I ask myself, why does this house exist? Why does it exist? Then when I'm talking about causes, I need to talk about all these different types of causes: material, formal, efficient, and final cause. So for example, if you want to understand the difference between proximate and remote causes, then here in the case of the builder, the proximate cause for the builder is he's going to get paid, or she's going to get paid. But the remote cause is me. I am willing to pay. I want a house built, so I want to pay this builder to build this. So that's how you can see about impetus and force as being the proximate cause. Right. So while discussing Newton's laws, it is important to keep in mind all these different types of causes, because when we are asking, what is something, we need to start from a 20,000 feet perspective, and then hone in and zoom in and go towards specific. So we start with the general approach of 20,000 feet view and go towards specifics. So to do that, our science should include our physics, should put physics first. This is physics, what we're discussing, and then equation. So that doesn't mean equations are less important. Equations are very, very important, as we have seen in the math that we just developed in chapter 1. And as we will see throughout the course, how much of math, how much of advanced mathematical concepts that we are going to use. But to understand physical thing completely, you need to put physical things first, physics first, right? And that's why all this is necessary to understand. And another thing that you should think about is, we're going to express all these equations in mathematics, which is what mostly we have done in chapter 1. We need to distinguish between the space that we talked about in that mathematics, that is mathematical space. So we need to make the distinction, but at the same time, also you want to note that mathematics is a tool, and based on symbols and the way we can manipulate these symbols. And so the mathematics itself does not include change. So remember the way we discussed the foundational principles. The first foundational principle was that things exist and things change. So there is physical change there. So mathematics itself doesn't directly include this change. For example, when I write, x of t is equal to vt, I'm treating, or if I were to plot this, right, let's say a car moving at constant velocity. Here I'm treating as if all these points, different points along the time axis, as if they're all coexistent, right? So when I say x of t is equal to v of t, this is for all t. So because it's for all t, it's static. It by itself is not telling you the physical change directly, because you're treating all these time points as if they exist at the same time, which is not right. And only when you refer to reality and actually go back to reality, for example, the car moving, right? Then I can see that I can see that if I go back to the car moving example, that then I know that it is, if I'm measuring this distance x, and if this car is moving, then this distance is going to increase over time, and that's going to increase linearly. And that's where, in that physical description, is where you see that, yeah, when I mean x of t is equal to v of t, this is how it is moving. So that physical picture includes the change. This curve itself is static. This x versus t itself is static because it's considering all these times existing as one, to put time on the same footing as space for mathematical convenience. So mathematics itself does not directly include change, and that's important to note here. And going back to Newton's equation, so Newton's second law is essentially F is equal to dp by dt. We ask the question, why do bodies need to move? For example, if there's a body A and if there's a body B, why does A need to move? Because, to interact with them directly, if a body A directly wants to interact with that body B, then it has to come next to it to interact physically. So when objects move, they can interact with each other, because when object A, for example, moves to a new place here next to B, then it is in contact with B, so it can physically change B, right? So that's why we are studying motion. And in mechanics, you must have studied different types of forces. For example, like, no force, F is equal to 0, right? Or gravitation, which is minus mgy. This is near the surface of the Earth, where treating gravity is a constant thing. So that's another thing. And then something like, in general, if I were to write for any two objects, I can write this as gmm by x square x. So what this is, essentially, it's a differential equation. So what we are saying here is that if I have, say, let's say I have Earth and there is Moon, I'm just drawing a one-dimensional picture here. And then if there is a distance x, then I'm saying that this force is minus gmm by x squared. And what Newton's laws are telling me is that this force is equal to dp by dt. So then I can write this as mx double dot. So x double dot means double derivative of dx with respect to time, right? So dp by dt is essentially mx double dot. So I have this differential equation that I set up, mx double dot is equal to minus gmm by x squared. So the thing to note here is that you're not seeing time explicitly here, but notice that this x is a function of t. So to solve this equation, of mx double dot, I need to know x of t, because x of t, how x is for t, to know x squared on the right hand side. So this equation is not solvable by integrating both sides directly, because I need to know what x of t is prior to solving the equation to find x of t, because my right hand side, that is this term, depends on it, right? And one thing to note is that the solution is true for all times. So at any x of t, if I take any t and then I have an x of t at that time, this equation holds true. So it is not just for one instant of time, but it's valid. This equation itself is valid for all times. So bearing this in mind, let's see some things that Newton left out. So when Newton looked at these forces, like the force of gravity, for example, like we wrote on the previous slide, here we have gmm by x squared, right? So in this, the objects are not touching each other. The moon is not in direct contact with Earth. Yet somehow, moon is able to feel the force, and same with Earth, right? And here we're looking at this mass is mass of the moon, because Earth is heavier, it doesn't move as much, because for the same force, it has more mass, so it doesn't move that much. So we're studying, the motion of moon. So that's how we have this equation. But this equation doesn't really tell how this force is going from Earth to moon, or in another way, if I say, if Earth goes off this instant, right? Then according to this equation, moon would feel that effect immediately or instantaneously, right? So if Earth were to disappear right now, then moon would feel that effect instantaneously, according to the Newton's law, because Newton really didn't consider what is in between. And this is actually a big problem in physics, because often people think that the space in between is nothingness. And we have so many terms in physics. For example, we sometimes say space, we sometimes call it vacuum, and nothingness, and we combine all these to often mean the same thing. We equate them, but that is not correct, because nothingness is non-existent. Nothing means no thing. It doesn't exist. But we have a symbol for it. It's a mental construct. It's a mental construct, like how in case of calculus, we completed the limit as a mental construct. Nothing is a mental construct. It is absence of existence. We know existence through our senses. We are able to see the physical world and we know existence. And if there are no things, the absence of things, we are able to know it only as a concept. So we have a symbol for that. Nothing is a symbol. As a word, it's a word that exists, right? Nothing is a word that exists, but nothing itself means non-existent. So nothing cannot exist if you truly think about it. So it is very easy to get confused between these things, because let's take a look at one of the recent documentaries that I have seen. I would like to show it here. So let's watch this one.
What is nothing? It's an extremely difficult question.
Let's look at the.
To answer, because if you think about it, wherever you look around you, there always seems to be something there.
What he's saying. I'll just keep quiet in case you're able to hear. But this part is the important thing.
This film tells the story of how we've begun to understand what is known as the void, or the vacuum, emptiness, or simply nothing. It's about reality at the very furthest reaches of human perception, a place where the deepest mysteries of the universe may be held.
If you didn't hear about it, I'll post the. I don't know if it got recorded because I'm recording on PowerPoint, so I don't know if the volume of the video was getting recorded or not. So if you didn't hear it, I'll send the link to you. And essentially what he says is that he's asking the question that, if you have a box, for example, he shows a box, right? If you take a box, right, and empty it, rid it of, all the molecules, right, and everything in it, you empty out everything in it, be it radiation, or be it any matter, or anything else, any dust, whatever you evacuate it, then he's asking the question of what is in it. And then he says that what is in it is the void, vacuum, and simply nothing. So he equates this empty space with vacuum, and then that with nothingness. But it is important to note here, it's not just a not just a correction in language, but it is we need to put physics first to understand physical things. So it's not just mere language difference here. Nothingness doesn't exist. It is not a nuance in the language, but we are when we are emptying everything out here, what is left is not nothing. It is something. And this idea that it was nothing actually came because Newton, in his formalism, oversimplified the mathematics. So not mathematics, he oversimplified the physics. So Newton, when he talked about space, he was talking about it as a mathematical space. And so mathematical space is an abstraction. So in this mathematical space, this is not the physical space really. We are abstracting out all properties. All properties we are abstracting out and we are turning them off somehow, and that's how we are able to have this mathematical space. This is not physical space. What you need to note is that physical space does not exist independent of physical things. So there is excessive abstraction in terms of what Newton did. So in fact, when Einstein came along, he saw that if I have a mass m, this mass m is somehow perturbing the space around it, and this perturbation propagates out. And if there is another mass here, that is going to feel this perturbation. And same thing with this mass. This mass is going to also perturb the space around it, right? So it is perturbing something around it. That is not nothing. It is something. And to avoid the confusion with vacuum, empty space, void, and nothing, we're going to call this something as plana. One should not mistake this to be mechanical ether. We're not talking about mechanical ether uh, uh, like in the case of Michelson-Morley experiments. This is not a mechanical ether. We're talking about the something, the space between the extension between these two masses, for example. And to avoid the confusion that it is nothing, we are calling it plana because it is something. And as Einstein showed it, you may have heard, you may have watched very famous documentaries or some sort of physics movies where they talk about space warps or space bends. How can it bend if it is nothing? It is not nothing. It is something. It's a physical thing, and it has properties. So plana, what is plana? Plana is a physical thing. So like any physical thing, it has properties, and those properties are fields. So this gravitational field that we looked at for this mass that goes around into plana, that field is a property of space. And this plana, you can define it as the non-massive substance between massive bodies. It is important to note that when we mean non-massive, we don't mean anything spiritual here. It doesn't have the quality of mass. It's a non-massive substance. It's still a physical thing. Plana is still a physical thing. It exists. It is physical. It changes. Like the gravitational field is perturbing this plana, and it's a non-massive substance between massive bodies. And we're going to use this because other words like space or vacuum lead to some sort of an issue in terms of the meaning. So in fact, this confusion becomes clearer if you go down to quantum field theory. So in fact, in quantum field theory, when we call the vacuum state, the vacuum state is not nothing. It is something. So Einstein corrected this excessive abstraction that Newton did through general relativity. And if you recall what we had studied in curvilinear coordinates, in general, if I have a vector r, which I can write as riqi, then we have seen that the line element dl square is gij dqi dqj. We have seen that in the last lecture where we discussed curvilinear coordinates. So this gij is the metric which is the solution to Einstein's field equations. So we will not be going into that, but the important thing to note is that plana is a physical thing, and that plana has properties. So these fields are properties of plana. Okay, so now let's look at charges, because we're going to be studying charges. So instead of calling them charges, we will call them properly what they are. They are charged massive bodies. What do we mean by this? We mean that if I take a massive body, charge is a property of that massive body. So if I have a massive body here, M1, that can have the property of charge. Similarly, if I have mass M2 here, this can also have the property of charge. But the plana in between, plana is non-massive. So plana by itself has no charge. Plana is charge-free, no charge. Because charge is a property of the massive bodies. And so here, what we're going to look at is how this charge, the property of massive bodies, can change impetus. Because if it changes impetus, then we know how to use Newton's equation. So we can, if I know what is the force coming from these, then I can go back to Newton's laws and look at how objects would move, right? And one thing to note is we as we are going to see, we will have charges that are positive and that are negative. So what does this actually mean, that positive and negative? This is a mathematical abstraction. They are not like like negative numbers. So, for example, if I were to take me walking around, right? If I take 2 steps to the left and then 2 steps to the right, then I am not moved overall from where I was, because I went 2 steps to the left, then came to the right, right? So to sort of encase that, we are going to call this as negative 2 steps, so negative x direction, right? And this has positive x direction, so I can write it as negative 2x or positive 2x in a mathematical fashion to show the thing that if I go 2 steps left and come back 2 steps right, I have not changed my position overall. But still, this motion, whether I go this way or this way, that motion is I am going forward in distance. Whether I go this way or this way, the distance is distance. That negative or positive is a mathematical symbolization we are giving distance, right? This distance going to the right is no special or no different from this. It's just our mathematical formalism that we have. So similarly here, positive and negative charges, we say positive and negative charges because charged bodies, charged massive bodies. So if I say charges, I usually mean charged massive bodies. These also produce some sort of perturbation in the plana. So if I were to put another charge here, this is going to feel the effect of the first charge. Similarly, the second charge would also produce perturbations in plana, which the first charge would feel. But if I were to place 2 different types, right, or before even we go to 2 different types, notice that from our experience, from our physical experience, we have seen that charged things can behave 2 ways. That they can be repelled away, they can be attracted, or repelled away. So this is unlike gravity, which is always attractive, where two things are coming along. And if we put these 2 things, this whatever is getting attracted if you put, say, a positive and a negative, then they transfer charge and become neutral. If you put them together, then they transfer charge and become neutral. And that's why we are sort of symbolizing it with positive and negative, but that doesn't mean there are only two types of charges, like that positive charge is different from negative charge. It's just like going to the right versus going to the left. It's distance, it's length. For example, if you go into quantum chromodynamics, where you're describing the strong interaction between protons. So protons are all of the same charge. So they are repelling each other away. But so there has to be some strong force that holds them, some short range force that holds them together. And there we have three types of charge. So there we have three types of charge, not positive and negative. So don't think that positive and negative charges are like positive and negative numbers. They're not different. It's just like going to the left versus going to the right. Now let's see, what happens when a charge disturbs the planar, right? So if I have a charge here, it's somehow interacting with the planar around it. So let's take at a distance r, let's take a sphere here, right? Now remember our discussion of divergence. So imagine that there is a water faucet here. Then water is flowing out. We would like to know how much water is flowing out. If there is a water faucet here, I'd like to know how much water is flowing out around the surface of radius r. Then, as we have seen, we can just do the flux, right? So whatever is the field that is at the center that is flowing out, that dot dA, where dA is the surface of the sphere at radius r, right? So if I do that, then I'm going to get this E dot dA. So I can write that as the electric field times, let's write this in polar coordinates maybe, or give me a minute here. Let me think about it. Yeah. So let's take a step back here. So E dot dA is going to give me the flux there. So then if I take it at some radius r, then this E, the surface area, is going to be the surface area, the total surface area of this. If E were constant, then you essentially have this dA. So this E times 4 pi r square, right? So if we look at if this is equal to some value, let's call it that value as some constant value c, right? Then this E times 4 pi r square is c, or E is equal to c by 4 pi r square. So whatever is field is in here, because of the surface area effect, if I take a larger radius, capital R, which is greater than R, then the flux E dot dA would be for that 4 pi r square. So there E at capital R would be c by 4 pi r square. And because of this surface effect, right? The charge affects the planar around it, which affects the planar around it, and so on and so forth. And as you go out radially, you are including more and more surface area without changing the source at the center. So it's like you have one faucet open here, water is flowing out. So as you go farther and farther from that faucet, you are decreasing the flux as per the surface area, 4 pi r square. And that's what you see as the 1 over r square in electric field. So if I have a charge q, then the electric field from that charge q is some constant k, q by r square. So from the general c by 4 pi r square, we come up with this kq by r square. So this constant has to do with what the environment is, right, where it is, and the source itself, you know, how strong the faucet is, right? If the faucet is putting out so much water, then you would have much more flux. So the strength of the faucet that is here at the center determines how much flux is going out. So this constant there depends upon how much charge is there at the center. So that's how we come up with this electric field, and this is pointing along the radial direction, because this water flow is going out radially, right? So now it's easier to see now that if I take divergence of E in spherical polar coordinates, we know how to take the divergence in spherical polar coordinates because from what we have looked at in chapter 1. So recall that the divergence in spherical polar coordinates we have seen for r over r square especially was 4 pi delta cube r. This we have seen it explicitly while discussing the Dirac delta function. So then if I do this divergence of kq by r square r, kq, I can pull that out. So I have kq, and the divergence of r square, 1 over r square, as we had seen, is 4 pi delta cube r. So we have 4 pi delta cube r. But this is considering electric field only at one point r. But if we want to integrate over all the electric field, then essentially we integrate over the entire space, right? We integrate over a volume element. So then we would have an integral here. So we would have delta cube integral. So essentially from there, we would get that Gauss's law from Gauss's theorem, which I'm getting ahead of myself. But what I want you to see is that the electric field goes as kq over r square because of the surface area effect. And this electric field is a property of the plana, and plana is not nothing because nothing is not existent. It is something, and all these fields are its properties, and that becomes more evident as we go deeper. But we will stop here, and in the next lecture we will get into Coulomb's law. Now that we have established what electric field is, we will get into Coulomb's law, and then we will rederive this Gauss's law again in more detail. I don't want to get ahead of myself, and then we'll also try to deal with continuous charge distributions. Thank you.